Good day, my name is Miriam Wooley, and I'm a Ph.D. student here at Arizona State University, and today I will be presenting on enzyme-induced carbonate precipitation for fugitive dust mitigation field trials in collaboration with industry. Enzyme-induced carbonate precipitation, or EICP, is a bio-inspired solution for mitigating fugitive dust on construction sites. When EICP is sprayed onto the soil, the chemical reaction forms a cemented soil crust by the process ureolysis, where the urease enzyme catalyzes urea in solution with calcium chloride to form calcium carbonate. The field trial objectives are to demonstrate the mitigation of fugitive dust by EICP technology at a field scale while developing the techniques of application, sampling, and monitoring. EICP treatment was evaluated in parallel to an industry-recommended dust control method of magnesium chloride and an untreated dry control plot. The level of treatment for EICP was evaluated in laboratory testing for resistance to wind erosion up to 24 meters per second. This trial was performed by student researchers in collaboration with industry partners of the Center for Biomediated and Bio-Inspired Geotechnics. The field trial is conducted in two phases. Phase 1 was a 43-day trial that was completed at the start of 2020, with the start of the second trial in 2021. Both phases are conducted at landfills in Arizona. Phase 1 was located in Apache Junction, Arizona, where the soil contained a high percentage of fines, identified as mostly silt, which is the particle size that is highly susceptible to wind erosion, and clay. The test plots were 100 feet long by 20 feet wide with 20-foot spacing and were parallel to each other. Treatment of the plots was completed in 2 days using an application system designed for EICP treatment. The EICP dual draw, or ED system, keeps the EICP component solutions separate and combines them in line immediately prior to the spray head to reduce clogging in the system. Monitoring included active air quality readings of PM 2.5, or aerosols, and passive dust collection samples of PM 10, dust particles. Multiple sampling episodes measured calcium carbonate and other ion contents, such as ammonium, for the soil crusts over the 43-day trial. A rain event occurred 6 days after treatment was completed, which formed a weakly aggregated soil crust in the untreated soil plot, and signs of overland flow in other plots were noticed. The natural background carbonate content of the soil varied between 2 and 5% by mass, which created a challenge in identifying increases due to EICP treatment, as the expected increases were only 0.7% for EICP times 1 treatment and 2.1% for EICP times 3 treatments. On average, EICP-treated crust specimens measured higher calcium carbonate contents than non-EICP treated soil, with the total measured average increases of 0.7% and 1.7% for each EICP treatment, respectively, for the first sampling episode. Average for the entire trial period over sampling episodes 1 through 3, the measured average aligns with the untreated value of 3.9%, however, with greater standard deviation between samples for EICP-treated specimens. This suggests a non-homogeneous distribution of calcium carbonate due to EICP treatment. For example, in one EICP-treated area, a higher clay content in the soil caused the treatment to pool, resulting in a white precipitate visible on the soil surface. This precipitate remained intact within this localized area through both rain events, indicating its calcium carbonate formed by the EICP treatment. Scanning electron microscope imaging, or SEM, of untreated specimens shows a single sand particle clad in finer grained particles. In EICP-treated specimens, amorphous calcium carbonate crystals clad the particle's surface along with salt, as noted by the yellow markings in the image. Air quality measurements were recorded for PM 2.5 with active clarity air sensors for less than and greater than 10 mph wind conditions. Data points were collected prior to treatment to establish a baseline, which is represented by the gray line in the figures and is compared to the post-treatment conditions represented by the yellow line. The red line marks the line of equality, where the untreated soil plot's response equals to that of the treated plot's response in reducing dust. Ideal conditions would result in the gray line below the red line and the yellow line above the red line, indicating a reduction of dust superior to that of the untreated control plot's response. However, since a rain event created a weakly aggregated soil crust in the untreated control plot, the EICP, magnesium chloride, and untreated control plots all measured comparable values for dust mitigation. These results tentatively show that EICP treatment is successful in reducing dust through formation of a soil crust, albeit heterogeneously forming a crust. The distribution of calcium carbonate precipitation is assumed to alternate between excess calcium carbonate precipitation and low to no precipitation throughout the plot. The level of treatment was evaluated for wind erosion resistance and appears to be insufficient for water erosion resistance. Recommendations for Phase 2 trial include redesigning the EICP treatment application system to include better in-mixing of the component solutions with separate pumps to set an equal flow rate, treating with a more aggressive EICP treatment for both wind and water erosion resistance, expanding sampling of the crust specimens, on-site weather monitoring, and measurement of potential dust emissivity of the soil surface using a portable in situ wind erosion laboratory or PI-swirl device.